All right. Okay, so on there, again, so for 4-1, we were looking at this first problem. We saw that our pattern there is that they are doubling each time, or they're multiples of, not multiples, powers of 2. So what I had just wrote on the board a second ago, that was 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power. So now we have 2 to the fourth power, which is how many? 16. So if I draw a picture real quick, draw a diagram, how many points should I have now?
16.
5, right? Because they added a point each time. So now, does it really matter where I put the point? Not really. I'm going to put it up here. So now I'm just going to draw all those lines in. So if we connect all of our points. Now you don't have to use a straight edge. I think I have all of them there. All right, so if we number them real quick, see, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Was our prediction correct? Yeah. So we found a pattern. We're able to see that the pattern works. It keeps going. All right. Now, the question here is, how is inductive reasoning used to recognize mathematical relationships? So, does anybody know what inductive reasoning is? What is inductive reasoning? Anybody? All right, so this is our first vocab word from this next section. Now I know I didn't have it posted before we started class, so putting it up there now. Inductive reasoning. It's a type of reasoning that reaches conclusions based on a pattern of specific examples or past events. How can you use inductive reasoning to determine what appears to be the next two items in each sequence? So, on here, inductive reasoning, you're using examples that are being given to you. Based on those examples, you're identifying a pattern that you think may work, and then you're applying it. All right? So, inductive reasoning is reasoning based on looking back, and it's based on observation. All right? So inductive reasoning based on observation. Right. Questions so far? All right. So look at the pattern. Now, these two are already done for us. These are the examples that are from the book. All right. And then there's some examples for you to try in just a moment. So looking at the numbers, look for a pattern. Observe that the terms decrease, and the difference of the first two terms is 6. So it goes down by 6. Then what happens again? It goes down by 6 again, down by 6 again, down by 6 again. So when looking for a pattern, remember to always test subsequent terms to be sure that you have found the correct rule. So again, we don't just want to look at the first set. We want to look at every single set together to make sure that pattern applies to everything. Could you have a pattern between the first two numbers and then the next two sets of numbers that didn't follow through to all the values? Is that possible? Yeah. So again, you want to make sure that you're double checking it works for all the numbers that are present. Now, this one, again, that one's pretty straightforward. The difference is 6 every single time. For the second one they give us, all right, The next two terms in the sequence appear to be, oh, sorry, I'm reading the top part there. Sorry, part B. So they give us a new sequence. Look for a pattern. Observe the terms increase by successive multiples of 2. So on here, we have going up by 2, going up by 2, going up by 2, going up by 4, going up by 6, going up by 8, going up by 10. So the number it's going up by, it's changing each time. Now, in algebra, you talked about sequences in series, and you probably even maybe wrote an equation for some of these. Does that sound familiar? Yeah. So you based it on either multiplication or addition, or you could have even done it based on if you didn't have the same pattern occurring here to here, but then looked at the numbers there. There's a common difference to what's happening each time, and that common difference is 2. So we could write equations based on that. That's going back to algebra. All right. But again, that's inductive reasoning, recognizing the pattern, applying the pattern. So you have the try it over there. That's on your paper. What appear to be the next two terms in each sequence? So take a minute, look at, see if you can find a pattern, and then we're going to see if you can identify the next two values in that sequence. Again, it could be a couple different things would work as an explanation there.
Oh, that's what you created. Oh, yes. That's what you created the YouTube video. That's hella smart. What? I'm like me. What?
All right, let's take a look at that first problem. So, on number 1, what appears to be the next term in each sequence? So, what do you think?
50.
All right, so you said 50, and what after that? 25. Now, I would say that's correct. What was the pattern? All right, so everybody agrees dividing by 2. Is that the only way to describe that? Is that the only way to describe that? So things that could have worked, we could say that we were dividing by 2 each time. Anything else? All right. You couldn't say maybe half, right? Like you're doing half each time. Or you could say maybe multiplying by 1/2 or multiplying by 0.5. Right? So there's other ways to describe that pattern, right? Is it the same pattern that I'm talking about every single one of those ways? Yeah. All right. So again, there's multiple ways that could work to describe this. Now, just looking at that, most of you guys probably said, oh, it's divided by 2. And that's fine. So now, on B, what would you say the next pattern, or what the next value in this sequence should be? You guys get stuck on this one? All right. Well, let's see. What's happening between here and here? Was there a value difference between these? So let's see. We had 18 and 24.
It added half of 18.
It added half of 18, you're saying? So half of 18 is 9. 9 plus, not half. You're on the right track, though. Huh? So here we added 6. All right. What did we do here? We added 8. What about here? Then it got confusing, huh? What about multiplication? Any of you guys think about multiplication? If we were to multiply, what would we have multiplied by here? well, it's 1/3 more.
1 and 1/3.
So 1 and 1/3. So if we multiply times 1 and 1/3 times 1 and 1/3, hey, that pattern looks like it might work, because then look at what the next one is. It's a fraction. Now, I could say 1 and 1/3, or I could change that over to 4/3. Right? That'd be another way of saying that. So if I multiply by 4/3 each time, that pattern holds true for all 4 of those numbers. So now if we take this number, let's do some math down here, multiply that by 4/3, what would my next number be? So, well, let's do, what's 3 times 3? All right, that's the easy part. 4 times 128. What was it? 512, you said?
Yeah.
All right, sounds good. Now, you could have done this many different ways. All right, make the numbers make sense to you. Just a quick reference here. This was 128. If I looked at that as, hey, that's 3 more than 125. 125 times 4 is what? That's an even 500, right? So then take that 4, that 3 that was left over. 3 times 4 is that 12. Again, you can use some number sense to break it apart, make the multiplication a little bit easier. That's if you don't have a calculator. All right? Now, I still need to do the next step. All right? So that's one of my answers. I got to take that now and multiply by 4/3 again. Now, these numbers aren't going to get any prettier. So the bottom number is 27. What's the top number?
2,048.
2,048. And hey, look at that. Break it apart. The 12 times 4 is 48. 500 times 4 is 2,000. So 2,048. Sounds good. And I don't think either of those numbers reduce. All right. Okay, let's move on. So, example 2. More inductive reasoning. Now, it says inductive reasoning to make a conjecture. Well, what's a conjecture? So this is another vocab word. There's a total of, I think there's 4 vocab words today. Hold on, let me flip back for just a second. Oh no, 3. Conjecture, counterexample, and inductive reasoning. Those are the ones that we're looking at today. So we've already looked at inductive reasoning. Now we're looking at a conjecture. So, has anybody heard of that word before, conjecture? So, a conjecture is an unproven statement or rule that is based on inductive reasoning. What conjecture can be made about the number of dots in the nth term of this geometric pattern? So, what we just did in that previous problem, we made a conjecture. We said, let me flip back. These values that we came up with, all right, dividing by 2, that was a conjecture. So the pattern is that we're dividing by 2 each time. That would be a conjecture. Now, in order to, so we're looking at, it hasn't been proven, and we'll get into proving things a little later on in these sections. All right. So again, a conjecture hasn't been proven. We've just taken what we've seen, saw that something applied to all those values, and then continued it on. So again, we're using a conjecture to figure out these patterns. So now, on this example, so we have the term, and we have the number of dots. So first term has 2 dots, second term has 6 dots, third term has 12 dots, fourth term has 20 dots. All right. And they gave us a little more information there. Write an algebraic expression to generalize the pattern for the nth term, since the number of rows in the pattern is equivalent to the number. Since the number of rows in the pattern is equivalent to the term number, use n to represent the number of rows. For the columns, notice you add 1 more each time than the actual number. So then you could say that you could find the total number by taking n times n plus 2. Sorry, not n plus 2, n plus 1. Or you could even simplify that. So again, this is algebra. So just like I said a second ago, n times n plus 1. Or if you simplify it, it becomes n squared. Yeah. Now, so n squared plus n. Again, that would be if you did that, distribute the n, and you get your pattern. Now, you have a try it. So let's see if we can figure out a pattern for these. How many dots are in the 5th and 6th terms of the pattern? So how many dots there? There's only one dot there, right? How many dots here? How many dots here? How many dots here? Now, does it really look like the numbers themselves have a pattern currently? No. But think about what they did over here. All right? Each time, if you look at the top number here, we had 1. All right? Then we had 2. Then we had 3. Then we had 4. So, can we break this down anywhere to figure out a pattern to what's going on? What do you think? Can we break it down similar to what they did in the last one? Two squared plus 1. All right. So
Feels like it's doing the squared part of the numbers and adding the last number.
okay. So we have 2 squared plus 1, 3 squared plus 2, 4 squared plus 3. All right. So essentially what you're saying is we have the number squared, so the term number, so I'm going to call that n, squared, plus, what's on top? How do we calculate the number on top? But let's not look at the first one for a second. Let's look at the other ones.
1.
So 1 is how many less than 2? 1 less than 2. 2 is 1 less than 3. 3 is 1 less than 4. So each time the top number was 1 less than the number of the term. Does this still hold true for that first one?
Yes.
Now, if you looked at that one, is it easy to develop this pattern using that first term? Not really, because there's not an extra point up on top, right? So now that we looked at the other 3, does it also apply to the first term? Yeah, it also works, because if I plug in 1 here, 1 squared is 1, 1 minus 1 is 0, 1 plus 0 is 1, which is what we had, 1 dot. So this looks like it works. So based on the number, we can figure out the number of dots given n squared plus n minus 1. Now, could I also simplify this a little bit? Let's see. Well, these don't have any like terms, do they? So n squared, this is just n, this is minus 1. On the last one, we could simplify it. But the last time, we didn't have a plus sign here, we had a multiplication symbol. Here, it's addition. We can't combine these. They're not like terms. So that's the only way to go. Do we have to have the parentheses? No. So we could also say n squared plus n minus 1. But that would be it. Those two would be two things that would work. If we wanted to find another value, say the 5th term, then you just plug 5 in for n, and you'd have your 5th term in the sequence. So again, sometimes you have to break it down into smaller values. Sometimes the pattern's not recognizable with one of the values at first. Here, the first term, it's hard to see the pattern. But when you look at only the other 3, and then check it with that first one, it also works. So it's good. That's a good conjecture. All right. So now using a conjecture to make a prediction. So again, this is the same thing that we just did, except we take it to the next step. We see if we can apply it. So actually find the next term. So over here on the try it, so you have to figure out a conjecture for these and then see if you can find that 5th term. Right. Go ahead and try that one. Right. I'll put this example up over here so you can see it. But again, you're trying to apply that conjecture now. So figure out a conjecture for the numbers that are there. Yeah. It could be a mathematical conjecture, like we did on the last one. Or if you want to write it in words, that'd be fine too. How many people have answers so far? Raise your hand if you have something that you think works. All right, let's go here first. What do you think works?
I'm not really sure if it
Okay.
works or not. Going from E to like between it goes 3 and then 4 and then 5 and then 6. So you would add the next one, like you would
So-
add 6 to 22.
So you're saying add 6 to 22. Okay. What do you think? Do you have something similar? Do you did it a different way? Same thing? Anybody do it different than that one? All right. Can you give me a way to describe that then? So some of you guys said that you have the same idea. How would you describe that? What are you actually doing then? Because you need to be able to express it in words somehow. So based on number year, if I wanted to find the 5th year, what am I actually doing? I'm taking
This is for homeroom tomorrow.
okay. No. Looks like we're getting back some FSA scores and stuff in homeroom tomorrow. So I'm guessing you guys will probably get your algebra FSA scores tomorrow in homeroom because these are the science FSA scores. Looks like for my class. But all right. Maybe it's just science. I don't know. I don't know. All right. Anyway, moving right along. Okay. So we had this increase. Now, if you just want to describe it in terms of what's going on there, that's fine. You could also set this up as an equation. So what I see as the pattern here, we had in year 1, we started with 10, right? So let's say I start with 10. Then each year after that, so in year 2, I had to add 3, right? So I'm going to add to this the number of the year I'm in plus 1 maybe. Let's see. Will that hold true for everything? Let's see. So we have 10. To get here, 2 plus 1 is 3. 3 plus 10 is 13. All right, go to the next one. Try it here. If I plug in 3, 3 plus 1 is 4. 4 plus 10 is, no, not quite. Something went wrong. All right. So I made a conjecture. It didn't work. All right. Sometimes a conjecture won't work. Just because it's a conjecture that you made doesn't mean it has to be true. Now, if I was trying to find the next number, I wouldn't be able to apply it like this. Now, it's okay if you can't think of a mathematical way of saying this, but if you want to say that each year you add one more member than the previous year you added, that's fine. Yes. Do you think of it?
For the year number, like for the first year,
Mm-hmm.
the second year, 3 comes out of it. For year 1, you just add 2. If you add 2 to the previous year, what it was, you get whatever.
Add 2 to the previous year.
So for the fourth year, going to the fifth year, you're adding 6. So you add 2, 4, you get 6. You got the previous.
So you're saying n plus 2? Alright, but it's still, that's, you're adding that to the previous number, right? So there's a couple different types of sequences and series that you guys talked about in algebra. There's one where it's based on the previous value. This would be like that type of sequence where like you could take the previous year's value and plug it in to get the next year's value. All right. So again, it's not as easy to set up an equation for this because you're setting it up based on the previous value. So there's the one where you actually plugged in the f of x from the previous year. Does that ring any bells? Yeah? Okay. All right. Let's go on. Let's keep going here. All right. Counter example. So this is our last vocab word. A counter example. Now, I don't know if is there a good definition on this page? Counterexample, oh, it's over there off to the side. Okay. So, essentially, a counterexample is something that proves that your conjecture is wrong, or shows that a statement is wrong, shows that it's false. So, it doesn't have to be false every time. It just has to be false once in order to make the statement false, right? So, if you have a bunch of examples, and you have a conjecture, and it works for most of the examples, that's fine, but if you can find one counterexample, one thing that makes it false, then it's wrong. So, again, a counterexample is an example that makes the statement or the conjecture false. All right? So, on here, the conjecture is a polygon with diagonals has 2 fewer diagonals as sides. Well, if you look at the 2 examples that they have over here, you have 4 sides, there are 2 diagonals. So it works there. All right? So that would be a good example, not a counterexample. But then if you look at a pentagon, if you draw all your diagonals into a pentagon, well, you actually now have 5 diagonals. Well, this statement originally makes it sound like we should have had how many diagonals? We should have only had 3, right? Because it said 2 less than the number of sides. Well, this isn't 2 less than the number of sides. It's the exact same as the number of sides. So this is my counterexample. Because it's an example that's proving that wrong. Right? So it's not just saying that it's false. It's the example itself that is proving that it is wrong. So anytime you're trying to prove something is false, you need a counterexample. So, on here, what is the counterexample that shows the statement of the sum of 2 composite numbers must be a composite number? Is false. So, testing and conjecture, same basic idea there. So, once you have a conjecture, you need to test it. See if there's a counterexample that would make it false. All right. So this is just a quick summary of everything that we talked about. So, inductive reasoning. Again, when you do inductive reasoning, you're going to observe a pattern and come to a conjecture. Then you can use examples to make that type of generation. It does not show that a conjecture is true. So I showed one example to you guys where I made a conjecture, but it wasn't true. So you have to look to see if there's any counterexamples to that to say, oh, that actually is not true. All right, it's false. Again, if you can find one counterexample, then it's not true. All right. Okay. All right. So what I want you to actually do for your assignment today, in your book there, I didn't write down the page numbers. It was 1 through 19. I just don't remember the page numbers. So,
28 through 31.
20 what? 28 through 31. So, page 28 through 31, 1 through 19. That's out of your student companion. Again, if you were using the textbook, it'd be the same numbers. It's just a different set of pages. So again, this is student companion for section, what is this? 1-4. All right, that's our homework for tonight. Now, it's just using those main ideas of counterexample, coming up with conjectures, all that stuff. So again, look over it, try it. It's a little bit different. After today, we actually moved from our idea of inductive reasoning to deductive reasoning.
Teachers and student parts is interrupted. At this time, teachers that are scheduled to be in the portable may return back to your classes at this